Number 40. Average atomic and molecular speeds, V sub RMS, are large even at low temperatures. What is the root mean square velocity for helium atoms at 5 degree Kelvin? Just 1 degree above helium's liquefaction temperature. All right, so we're talking about helium. What's liquefaction? It's just when vapor turns to liquid. Don't worry about what it is, though. So what we need to do is we need to know a relationship between the root mean square velocity and the temperature. All right, so the prior problem, number 40, dealt exclusively with this. We have a formula here that looks just like this. V sub RMS is equal to the square root of 3 times the Boltzmann constant times the temperature, all divided then by the mass of a single molecule. If you're wondering where this equation came from, check out my general video on kinetic theory of gases. I explain all about it. All right. I'm going to leave a link in the description below for that. So what we have is we do have the temperature. That's simple. K is a constant. That's the Boltzmann constant, 1.38 times 10 to the minus 23. The only thing we realize is we don't know the mass of a molecule, right? Or an atom. It depends on what we are talking about. In this problem, we're talking about helium atoms. All right. So how are we going to find the mass of a helium atom? Well, you'll have to go to the periodic table first. And you'll realize that when you look up helium on the periodic table, you'll realize that its mass is about 4 grams per mole. Okay, so what I need to do actually is take this value, 4 grams per mole. I'm going to write it down here. We're going to have 4 grams per, how many moles per 1 mole, right? Anytime you have per something, it's always per 1 of that something. And somehow we're going to have to take that and convert it into kilograms per atom. All right, because I want to know the mass of a single atom. That's what the M here represents. So how do we do that? Well, let's work with 1 unit at a time, okay? So let's first get rid of the grams in the numerator. And by the way, why do I need kilograms? Well, because that's what mass is in physics, right? You plug in kilograms into your formulas. So in order to cancel the gram over here, which originates in the numerator, I better place it in the denominator. Now I'm thinking, do I know a relation between kilogram and gram? Of course I do, right? It's 1,000 grams per kilogram. And guess what happens to the grams? Toodaloo. Now, I now would have kilogram per mole. If that's what I needed, I could stop here, but I don't. I need kilogram per atom. So if I want to cancel the mole now, and the mole originates in the denominator, where must I place it in this fraction? Good. In the numerator. I'm just guessing you got it right. I'm sure you did. All right, so we put it in the numerator, and now what then goes in the denominator? Well, I know I want to convert this to atoms eventually, so I'm thinking, could I do that now? Meaning, do I know a relationship between mole and atom? And yeah, it's basically Avogadro's number, 6.02 times 10 to the 23rd. That many atoms in a single mole, okay? You might be used to seeing this number, you know, as in terms of molecules per mole, and you might be saying, how can it mean 2 of the same thing? Well, it basically just, it's like a mole is like a dozen. Right? If I said, you know, how many's in a dozen? You would say 12. Okay. So that's like saying 1 mole is this number, right? 1 dozen represents 12 things. 1 mole represents this many things. Okay. Then doesn't it kind of also depend on what thing you're talking about? Right? 1 mole of eggs would be, 1 dozen eggs would be 12 eggs, right? 1 dozen bricks would be 12 bricks. 1 mole of helium atoms then would be equivalent to 6.02 times 10 to the 23rd atoms of helium, okay? 1 mole of oxygen molecules would be equivalent to 6.02 times 10 to the 23rd molecules of oxygen. It depends on what you're talking about. All right, I know it's confusing though. I'm not saying it's simple. I was there once before too as a student, so I do understand. So let's do the math here. 4 divided by then 1,000 multiplied by 6.02 times 10 to the 23rd. And we're going to get a value now of about 6.64 times 10 to the minus 27th. All right, and that's basically kilogram per atom. And that would be the mass per atom. Okay, so that's what we need. So now we have everything we need in order to solve, right? So the root mean square velocity, I don't know why there's 2 R's there because the pen is lagging. V sub RMS is going to be cube root. What is that? That's not a cube root. That's a square root. It's a square root. I'm looking at the 3 over here and thinking cube, but it has nothing to do with that. 3 multiplied now by Boltzmann constant of, let me leave out that little dot. 3 times then 1.38 1.38 times 10 to the minus 23rd, and then multiply that by the temperature of 5 Kelvin, all then divided by here, the mass now, 6.64 times 10 to the minus 27th. And we can now calculate V sub RMS. Take out the calculator. Square root of 3 times 1.38 times 10 to the minus 23rd times 5. Divide that whole thing by now 6.64 times 10 to the negative 27th. And I get about 177 or so. How many sig figs? Looks like 3. So about 177. Whatever. 177 meters per second. And that would be the speed of those particles. So even at almost close to absolute zero here, the particles are still moving at 177 meters per second. So, yeah. All right, guys. Thanks for tuning in. Appreciate it very much. Please remember to help us out. All right, subscribe. That would be awesome. Tell your friends and maybe hit the like button if it helped. Thank you.